All right, today we are looking at section 1.4, which is relating polynomial functions and equations. So essentially what we're going to be doing is looking at the patterns of various polynomial functions and equations to see the end behavior of our graphs, and then we'll do some practice graphing utilizing that end behavior. So first we have a definition of polynomial functions. Polynomial functions are functions that can be written in the form f of x equals a subscript n, x to the power of n plus a subscript n minus 1, x to n minus 1, and so on until we get down to just a0, and this should have been x to the 1. So essentially what we see is we have exponents that are decreasing by 1 each time. So if our n was 5, we'd have x to the power 5, x to 4, x to 3, x to 2, x to 1, and then x to 0 technically, which is 1. So 1 times anything is itself. And our a values are just our coefficients. Now we have a restriction that n is a whole number. And the coefficient of the variable for largest exponent is our leading coefficient. So this a subscript n out front, because it's with our largest exponent, is our leading coefficient. Now our leading coefficient is going to be critical in terms of where our graphs start and end. And we can also say the graph of a polynomial is smooth and continuous. So by smooth, it means that essentially we don't have any sharp places where it turns around. It's continuous in that it doesn't have any gaps. So something not smooth, for example, could be, say, a sawtooth graph. So this would not be a polynomial because we have these sharp places where it turns around. And continuous, we may in the future deal with graphs that look like this, where you have a gap between them. So that also is not continuous. So polynomials are smooth and continuous. So we can see essentially they have a value of y for every x value, and we're not jumping from one y value to another. Now we're going to look at various degrees of polynomials and find some patterns of them. So a degree polynomial, or sorry, degree 1 polynomial is a linear function. It's technically an odd degree because our degree is 1, which is odd. So if we have a positive leading coefficient with a linear function, our graph is going to look something like this. Because remember that if we have y equals mx plus b, essentially, as long as this is positive, we're going up as we go to the right. If we have a negative leading coefficient, it's going to go down as it goes to the right. So we'd have a graph that looks something like this. Next, we have our quadratic. So you would have dealt with quadratics in grade 11. So quadratics are degree 2 because our largest exponent is a 2. Now, because 2 is an even number, technically that's an even degree polynomial. So if you remember from quadratics, essentially they open upwards or downwards. If there was a positive in front, they open upwards. So this graph would look something like this. Now with quadratics, if our a value in front, our leading coefficient is negative, they open downward. So this one would look something like this. So next we will start looking at some ones that you have not dealt with in previous grades yet. Okay, so the next one is a degree 3. A degree 3 function is a cubic function, so it has its largest exponent as a 3. Technically, that's an odd degree because 3 is an odd number. Now, if I graph this function here, I get something that looks something like this. Now, if I have a cubic function with a negative in front and this equation, I get something that looks like this. So that is a cubic function. Our degree 4 is known as a quartic function. So it's even degree of a highest exponent of 4. Now this first one, if I graph, will look something like this, where for one with a negative in front, it's going to look something like this. Last one we're going to look at is a quintic function, so degree 5, an odd degree polynomial. So largest exponent is a 5. If I graph this first one, it's going to look something like this. And if I graph the second one, gives me something that looks somewhat like this. So what we're going to do next is look at some patterns with all these graphs. So one thing that you may have noticed as I was drawing these out is our maximum amount of hills and valleys is equal to 1 less than our degree. So for example, this is degree 5. We've got 1, 2, 3, 4 hills and valleys. 1, 2, 3, 4 hills and valleys. We have, for degree 3, we've got just 2, or we could potentially have none. Quartic, we have degree 4, we have 3 hills and valleys. So our maximum amount of hills and valleys is going to equal our degree minus 1. So if we go further up, our quadratic, 2 minus 1 is 1. So we've got 1 valley here, 1 hill here. Linear, 1 minus 1 is 0, which we have a straight line, so we don't have any hills or valleys. What we'll look next is at the patterns between our odd degrees and even degrees, as well as our leading coefficients. So we can see, for example, this is an odd degree of a positive leading coefficient. We start here and here. Once again, odd degree, positive leading coefficient, we start here and end here. Same with this one, odd degree, start here and here. So essentially everything that's odd degree will have that same pattern. If it is a positive leading coefficient, it will start down here and it will end up here. If it's negative, it's going to be the opposite. So it's going to start up here and end down here. So starting up here, ending down here, start up here and down here. Next, we'll look at the patterns of our our even degrees. So our first one we look at is our quadratic. If it's positive, it looks like we have something that starts up here, ends up here. If it is negative, it starts down here, ends down here. Next, even degree. If it's positive, we start up here, ended up here. If it's negative, we start down here, ended down here. So essentially our even degrees just follow our basic rules that we had for our quadratic, which is if it has a positive leading coefficient, we're going to open upwards. If we have a negative leading coefficient, they're going to open downwards. So next we'll look at how we can put those patterns into descriptors. So if we have an odd degree polynomial and we have a leading coefficient that's positive, we'll talk about what our end behavior is. So what we'll say is as x goes towards negative infinity, so in other words, as we go towards the left side of our graph, y is going to go towards negative infinity. So it's going to be down towards the bottom of our graph. Now, as we go to the right side of our graph, so as x goes towards positive infinity, y increases, so it goes towards positive infinity. Now, if we have a negative leading coefficient, we started fairly high, and as we moved to right, we decrease. So as x goes towards the left side of our graph, y increased towards infinity, and as we move to right, so as x went to positive infinity, y went downwards, so it went to negative infinity. Next, we'll look at our even degree polynomials. So for even degree polynomials, they acted just like quadratic. So if we had a positive leading coefficient, they opened upward. So we can say that as x went towards negative infinity, y went towards positive infinity because it went upwards. And then as we go to the right, so as x goes towards positive infinity, it also went upwards, so y went to positive infinity. For negative, they open downwards, so as x goes towards negative infinity, y also goes towards negative infinity because it's going down. And as x moved to right towards positive infinity, we once again went downwards, so we went to negative infinity. Now, so far in the workbook, they've referred to places where a graph changes direction as hills and valleys, but we'll go into a bit more specific naming of them. So a point where the graph changes from increasing to decreasing is referred to as a local maximum. So if, for example, this was our graph, we can have multiple local maximums. Now, a point where the graph changes from decreasing to increasing is referred to as a local minimum. And just like local maximums, we can have multiple local minimums. Okay, so this brings us to the graphing section of these notes. So we have three main ways to graph. One is table of values, which you should be familiar with from the past, but we'll do a couple examples of that. We also have using our intercepts, so both our x and y intercepts. And then we'll also go into multiplicity of 0, which we still utilize our intercepts, but it's what happens if one of our factors repeats itself. So table of values, you should know from the past. It's essentially use a table of values, substitute x values in to get our y values. So we'll do an example of that. So graph y equals x cubed minus 3x squared plus 2. So we'll set up a table of values. And let's say go from -3 to +3. So we have y is equal to x cubed has 3x squared plus 2. So for the first one, we have -3 cubed minus 3 times -3 squared plus 2. So that's going to give us 52. So that's way off our graph, so we won't plot that. I'm sorry, that should be -52. Next, we'll substitute a -2, so we've got -2 cubed minus 3 times -2 squared plus 2. And that gives us -18. So it's still probably not going to fit on our graph unless we change our scale. We'll go to -1. So we have -1 cubed minus 3 times -1 squared plus 2. And that brings us to -2. So at -1, we are at a y value of -2. Next, we'll put 0 in. So we've got 0 cubed minus 3 times 0 squared plus 2. So that gives us a value of 2. So at 0, we are at +2. Now, that's our y-intercept. You'll also notice that that's our constant term of our equation. So this is always going to be our y-intercept because our y-intercept occurs where x equals 0. So every term that has an x in it will disappear when we plug in an x value of 0, leaving just our constant term as our y-intercept. Next, we have 1 cubed minus 3 times 1 squared plus 2. So that gives us 0. So at 1, we are at 0. Next, we have 2 cubed minus 3 times 2 squared plus 2. And that gives us -2. So at 2, we are at a y value of -2. Next one, we have 3 cubed minus 3 times 3 squared plus 2. And that gives us +2. Now, based off of the fact this is an odd degree, positive leading coefficient, we know we should be starting down here, ending up here. Because it's a degree 3, we know we have a maximum amount of places it turns around is 2. So we'll just draw this in because we probably have enough points to represent that. So as you can see, utilizing our points we have, we are starting down low like we would with an odd degree with positive leading coefficient, ending high, and degree 3. So we have a maximum of 2 places where our graph turns around. Okay, so next we are looking at utilizing our intercepts. Now, when we're graphing using intercepts, for most of the time, it is usually quick sketches in which the graph is not always super precise, other than that we have the locations of our x and y intercepts down. So our y values between those may not be correct, but it gives us an idea of what our graph should look like. So with intercepts, we treat it just like we did with quadratics in grade 11, where if you had a quadratic and factored it from those factors, you could get your x-intercepts. With any polynomial, you can do the same thing. It's just your amount of x-intercepts is going to depend on your degree. So we'll fully factor a polynomial to get our x-intercepts. After that, we get our y-intercept from our constant term, mark all those points on our graph, and then we use our knowledge of our end behavior to figure out where our line should go. Okay, so first graph we have is f of x equals x cubed plus x squared minus 6x. So first thing I would do is factor out an x, because every term here has an x. So we've got x times x squared plus x minus 6. And then this is a quadratic side product sum factor it utilizing knowledge from grade 11. So we're looking for 2 things that multiply to -6, add to +1. So that would be +3 and -2. Now, if we look at this, we have x-intercepts at 0, -3, and +2. So I'll mark those out. So I've got x-intercept at 0, I have another at -3, I have one at +2. And in this case, we don't have a constant term, so that's the same as saying plus 0. So our y-intercept is at 0, which we already have an x-intercept there. Now from this, we can see we have an odd degree because it is degree 3. We have a positive leading coefficient. So from the patterns we looked at earlier, we know odd degree positive leading coefficients should start down here, end up here. So we will just quickly draw in a graph. Like I said, we're not really too concerned about our points between these x-intercepts. Using our x-intercepts is just a quick way to sketch roughly what our graph should look like. Okay, so we'll do another graph that takes a little more factoring to do. So we have 2x to the power 4 minus x cubed minus 14x squared plus 19x minus 6. Now this is a degree 4, so we can expect up to 4 x-intercepts. Okay, so when figuring out possible factors of this, we need to look at our factors of -6. So that'd be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So I'll try with an a value of 1. So I'll just quickly rewrite my equation. So I've got p of x, or I guess in this case f of x, is equal to 2x to the power 4 minus x cubed minus 14x squared plus 19x minus 6. Now, what I'm essentially going to do is utilize the theorems we went over earlier in this chapter. So first, utilizing remainder theorem, in which whatever a value we plug in for x gives us what our remainder would be if we were dividing that polynomial by x minus a. And then we'll also use our factor theorem, in which it states that if our remainder is 0, it is a factor of our polynomial. So I'm going to see if I just divide this by x minus 1, if I have a remainder of 0, and if so, that would be a factor of it. So if I have f of 1, that gives me 2 times 1 to the power 4 minus 1 cubed minus 14 times 1 squared plus 19 times 1 minus 6. So that would be 2 minus 1 is 1. Minus 14 is negative 13. Plus 19 is positive 6. Minus 6 is 0. So because that's 0, we know that x minus 1 is a factor. Now, because it is a factor, I'm going to divide it out of here using synthetic division, and then we will start factoring what's remaining. But if x minus 1 is a factor, I might as well mark that x-intercept. So I'll be an x-intercept of positive 1. So synthetic division, we're utilizing our coefficients. So we've got 2, negative 1, negative 14, 19, and negative 6. Now our a value is 1. We bring down the first term, multiply it by the 1. So that's 2, add these, so that gives us 1 multiplied by 1, gives us 1 here, which will give us 13. Multiplied by 1 gives us 13 here. Or sorry, negative 13 here. So negative 13 here, adding these gives us 6. Multiplied by 1 gives us 6 here. As expected, we have a remainder of 0. So we now have 2x cubed plus x squared minus 13x plus 6 plus 0. Or sorry, we don't need that plus 0 part. So we are now going to factor this. So this has the same a values as we had here. So sometimes factors repeat. So I'm going to try a is equal to 1 again. So if I'm using a is equal to 1, that gives me 2 times 1 cubed plus 1 squared minus 13 times 1 plus 6. So that'd be 2 plus 1 is 3, minus 13 is negative 10, plus 6 would be negative 4. So that is not going to give us an upper factor. So we'll try a is equal to negative 1 now. So we have 2 times negative 1 cubed plus negative 1 squared minus 13 times negative 1 plus 6. So negative 1 cubed is negative 1 times 2 is negative 2. This is going to give us positive 1. So negative 2 plus 1 is negative 1. Plus 13 would be 12, plus 6 gives us 18. So this also doesn't work. So we'll go on to the next one. So we've got an a value of 2. So we have 2 times 2 cubed plus 2 squared minus 13 times 2 plus 6. So 2 cubed is 8, times 2 is 16, plus 2 squared, which is 4, so 16 plus 4 is 20, minus 26 is negative 6, plus 6 is 0. So we have found a factor. So we can say that x minus 2 is a factor. Now that means we're going to have an x-intercept at positive 2. And then I'll do synthetic division again. And then we'll factor the quadratic that we'll have remaining. So we have an a value of 2. Using our coefficients from here, we have 2, 1, negative 13, and 6. So we bring down the 2, multiply by 2 is 4. Add these, we get 5. Multiply by 2, we get 10. Subtract them, we get negative 3 times 2 is negative 6. So essentially, what we have remaining is 2x squared plus 5x minus 3. Now we'll do a modified product sum. So our product would be 2 times negative 3, so negative 6, with a sum of 5. We'll start each bracket with 2x. And then two things that multiply to negative 6, add to 5 would be positive 6, negative 1. We have an extra factor of 2. We have to divide out one of brackets. So that gives us x plus 3 times 2x minus 1. So from that, we're going to have x-intercepts at negative 3 and 1/2. So we have one at 1/2 and at negative 3. Now looking at our equation, that's our y-intercept. So our y-intercept is at negative 6. And we have an even degree that's positive. Which means it opens upwards. So we'll be coming down from here. Make sure we get through that y-intercept, go back up, go through the next x-intercept, and then back up through the last one. So we have our degree 4, which has 3 places where it changes direction. So you'll notice in these examples so far that we've graphed, both for table values and factoring, our amount of times it's changed direction has been exactly one less than our degree. Next, we'll look at situations where that is not the case. So with these, it's referred to as the multiplicity of 0. And we use this if one of our factors occurs more than once. So if we've already factored it and we have something like y equals x minus 1 squared times x plus 2 cubed, this has what's known as multiplicity of 0. It's referred to a multiplicity of 0 because technically zeros are x-intercepts, and because we have identical factors, we have multiple factors giving us the same x-intercept. Now this one we would say has a multiplicity of 2. And this one has a multiplicity of 3. So essentially our multiplicity number is just our exponent. Now, if the multiplicity is an even number, depending on which direction we're coming at our axis from, it'll look slightly different, but essentially mirrored. If it's an even number, the graph touches our axis at our intercept point, but does not cross. So if we're already above our x-axis, it's going to come down, touch our axis, and turn around. If we're below our x-axis, it's going to come up, touch our axis, and go back down. Now, if the multiplicity is an odd number, it's going to curve like it does for the even ones. However, it is going to still pass through the axis. So it can look like this first one where we're curving towards the axis and then it passes through, going from a low value to a high value, or we can go the opposite way, high y value down to a low y value. Okay, so we're being asked to graph f of x equals x plus 1 to 4 and times x minus 2. So looking at this, we can write out our x-intercepts right away. So we've got -1 and +2. Now this is an even multiplicity. So that means we know that where we're at -1, it's going to touch our graph but not cross through. We can also get our y-intercept. To get our y-intercept, we know that's where x equals 0, so we can just put zeros in for these x's. So that'd give us 1 to the power of 4 times -2. So 1 to the power of 4 is 1 times -2 would give us a y-intercept of -2. Now, to get our degree, we can just add up our factors. Now, because this is this factors to the power of 4, essentially this has 4 factors. They're all identical. Plus we have this additional one, so this is a degree 5. Now we'll also notice that there's no negatives either in front of here or in front of any of x's. So we know that this is going to be a positive leading coefficient. So if it's odd degree positive leading coefficient, that means we're starting down here and ending up here. Now that first x-intercept, the -1, is the one with multiplicity, so it has even multiplicity. So when we reach it, it's not going to cross the axis, it's going to turn around. We'll go through our y-intercept and then back upwards. Now, this was degree 5, so we could have had up to 4 places where our graph turned around. But because we have factors that are repeating, we have less points where it turns around. Okay, so we'll look at one last example. Graphing f of x equals -x plus 1 cubed times x minus 3. So looking at this right away, we have x-intercepts at -1, which has an odd multiplicity, which means it's going to pass through our axis. And at positively, Now, to get our y-intercept, once again, substitute 0 in for x's. So we have 0 plus 1 is 1, 1 cubed is 1. We have a negative in front, so it becomes -1 times -3. So our y-intercept is +3. Now, if we add these up, we've got 3 factors here, 1 factor here. So this is a degree 4, which means it is even. We have a negative in front, so that means we have a negative leading coefficient. So we expect it to open downwards. So we should be coming from down here. Now, like I said, this first x-intercept is an odd multiplicity, so it's going to curve towards our axis and then curve back through. And our graph will look something like this. Okay, so that is it for notes on this section.